right? Shall I start?
Yeah,
Okay.
absolutely.
Okay, thank you. I'm I'm grateful to the organizers, Igor and Vadim, for their invitation. I'm Qing-Dong Jiang from TDD Institute. So I will talk about cavity quantum materials. I will not talk about 4E. So it's a little bit deviated from the main topic. You can treat it as a fika, okay? So, okay. If you don't know what is a TDD Institute look like, okay, here's a picture. It's like two chopsticks, having a egg in between. So here's my outline. I will first talk about vacuum and the famous effect induced by vacuum quantum fluctuations, the Casimir effect, as an introduction. Then I will talk about the quantum manosphere. The concept came up with me and my collaborators. Then I will move to this cavity quantum matter. The last part is a summary. So here's the main point of this talk. Okay, so people find that using light, shining light to the materials, can tune a lot of the properties of materials. But in the recent years, people want to shift to different paradigm. So by reducing the number of photons, but increasing the light-matter interactions. So with this, for instance, in the extreme case, in the vacuum, but using the cavity can enhance the light-matter interaction in the vacuum, so that they can use the cavity to change more properties of materials. So we have a lot of advantage comparing to the shining light. For instance, there's no heat, okay, and it's an equilibrium approach, and they can strong light-matter copy. So you don't need light, okay? You're using the cavity vacuum. You can still doing a lot of things and avoid this the drawbacks of the lasers. So with that, I want to say that okay, it's less is more, okay? we know a lot about more is different, but I want to say less is more here because you can achieve the same thing with the less gradient, and usually that's better, okay? Achieve the same goal with a little gradient, that's better. So here's the words from this guy. So less is more only when more is too much. Shining light is too much photons. So quantum fluctuations in the vacuum, it's because of the uncertainty of principle, okay? So the fields, the particles, popping in and out. And for instance, in the vacuum, even the electric field average is 0, but the fluctuations is non-zero. So that kind of quantum fluctuations give many interesting effects and very important effects. For example, Lam shift, you all know that it's giving the birth of the quantum QED, and this anomalous magnetic moment also from the quantum fluctuations. The spontaneous emissions also from the quantum fluctuations. For instance, if electron in the eigenstate, the eigenstate's lifetime is infinity, but it's not. The electron is not isolated. It's interacting with quantum fluctuations in the vacuum. So it has make the level has some broadness, and that's why it's a finite lifetime. And the Gurkle climbing, why this Gurkle can climb on the wall is because of van der Waals force, which also coming from the quantum fluctuations of vacuum. And the Galilee formation, Hawking radiation, cosmology constant, these topics also relate to this vacuum quantum fluctuation. Okay, but when you mentioned quantum fluctuations in vacuum, so one of the most important effects is the so-called Casimir effect. Actually, there's a classical version of Casimir effect. So in ancient people, the sailors know that they cannot make the two boats, two ships, too close to each other. Otherwise, these two ships will attract each other, even though there's no wind. So this is the so-called classical Casimir effect. And that's because of the fluctuation of the sea, the waves in the sea. But in the vacuum, there's no water. However, the vacuum has a lot of quantum fluctuations. We can think of vacuum as the quantum fluctuations as a sea of quantum fluctuations. So the van der Waals force is induced by these quantum fluctuations of EM fields in the vacuum. It has some temporal electric dipole, these fluctuations, and make them attract each other. And for two plates, if you put two plates in the vacuum, because of the quantum fluctuations, these two plates will talk to each other and they will attract each other. Such attraction is very strong because if you put two plates 10 nanometer away from each other, the pressure is about 1 atmosphere. 1 atmosphere pressure means that you have 1,000 kilograms water on top of 1 centimeter square area. So that is very crucial when you make the devices very small. And there are two ways to understanding the customer force. So one way is from the boundary condition, very classical, just counting mode. The other way is from the quantum field theory. So imagine that one plate sends a vertical photon to the second plate, and the second plate sent back. It's a second order perturbation of quantum field theory. And this kind of this force actually already been observed in experiments by different methods. Because of time, I won't go into the details. It has been long measured and precisely measured. But there's a very important theorem in this field, so-called no-go theorem, showing that if these two things are mirror image of each other, that means there's a parity symmetry of these two things, then the force is always attractive. However, attractive customer force will make things stick together, so it's not good for nano devices. And the people want to make it repositive, but how? This is a very important problem. So actually, in early days, theory by Lifshitz already found that if you have 3 materials with 3 different dielectric constants, if these 3 dielectric constants increase, one by one, then you have repositive customer force. So this has already been verified in experiments. Okay, so this configuration of gold, liquid gold, this configuration is just normal configuration. It's attractive, but gold, liquid, and silica, the dielectric constant decrease monotonically, and then it is a repositive. So in recent years, the quantum Hall system, new materials, topology insulators, chain insulators, well-sand metals, a lot of different materials are proposed to realize repositive customer force. But all these forces are really small. A few, 3 orders smaller than the normal customer force, because most of the systems are insulators. Insulators have very little influence on the boundary conditions. So this is many orders smaller than the customer force between metals. Here in this work, we found a way to realize repositive customer force, so as strong as the attractive one. So what do? We just insert a carrier materials between these 2 metallic plates, and then we find that this carrier materials can give rise to a carrier vacuum. That makes the force will be repositive. And by carrier materials, I mean the materials break parity symmetry. Okay, I can answer a question in the question section. So I don't want to go to details, but this force is enhanced. It's as big as the normal attractive customer force, but it's repositive in this case.
Sorry, but this is different than the Lifshitz mechanism that you explained?
Yes, Lifshitz means that 3 materials, but here.
Oh, there's still 2. This is vacuum? Or
yeah. We only insert a carrier materials between this A and B. A and B can be the same materials.
Oh, I see.
So Lifshitz needs 3 epsilon. Yeah.
Have 3 materials from the Lifshitz theory been studied experimentally?
Yes, I just showed that this is experimental.
Okay, thank you.
They verified 3 materials. Yeah, but if I have nano devices, what do? I just insert a 3rd material to make it repositive. That's much easier.
Mm-hmm.
So I showed that these parity materials, carrier materials, that can make repositive customer force. But in nature, there's another symmetry breaking, very important. Temporal symmetry breaking. So what kind of temporal symmetry breaking combining with quantum fluctuation give some really interesting effect? That's the next topic. And that's we came up with the idea about, we call it quantum atmosphere. Okay, so we know that quantum magnetic field can make very interesting quantum effects. One of the effects is so-called quantum Hall effect. That's the orbital part. The other is the spin effect, because the Zeeman splitting of spin in the magnetic field. And question is, do we really need magnetic field to achieve this effect? Well, no. Well, in 1988, Deng and Haodan found that, okay, even there's no magnetic field, no magnetic fields, you still can achieve the quantum Hall effect. And in this quantum atmosphere paper, we show that even though there's no magnetic field, you can still achieve Zeeman effect. Because in all these works, the essential thing is time of symmetry breaking. It's not magnetic field. Magnetic field can be zero, but still there is time of symmetry breaking. So why do we call it quantum atmosphere? Because we want to, analog a classical atmosphere of the Earth. It can reflect, the atmosphere of Earth can reflect some properties of our planet. It's like similar in the vacuum close to the materials can reflect the symmetry properties of the materials. Okay, that's why we call it quantum atmosphere. And so, okay, let's calculate his example. So we assume a spin close to a chain insulator. And now, because chain insulators don't generate magnetic field, okay, so we can calculate how much this spin split because of the quantum fluctuations close to the chain insulator. And I will skip the calculation. It's the one loop Feynman diagram. So if we do the calculation, you will find if the electron is 10 nanometer away from the chain insulator, it will get the effect splitting like 10 Gauss magnetic field induced. So that's a pretty big effects and should be measurable both in NV center STM experiment, spin polarized STM experiment. And to further generalize, extending our idea, we are not only talking about the time of symmetry breaking, we want more. We want the vacuum close to the materials reflects all kinds of symmetry breaking. Okay, this is the first order of the gradient field. That's all that you can write down these polarizations. Okay, so you know this. The first column is what you learn in the textbook. Second column is you learned in the electric magnetic coupling materials and topological materials. And the other thing is what we wrote in this paper, that you can induce more kinds of combination of symmetry breakings and generate different kinds of quantum atmospheres.
But what can you say? What's required for the new ones that you discovered?
Well, for instance, to guarantee some terms, you either needs time of symmetry breaking or needs parallel symmetry breaking, or needs both. So there are different kind of combinations. So, so this experiment paper is not the experiment that verify our original proposal, but it's a proof of principle experiment that they can showing that they can detect quantum fluctuation of spins, and they say that our quantum atmosphere probe is different from all the previous one, that you're shooting a real particle to materials to detect it. Here we do not shoot particle into materials. We're using the quantum fluctuations. It's two particle process. So this has advantage compared to previous ones. Yeah. So I think I'm a little bit too fast. So okay, now I want to slow down. The symmetry breaking and the quantum fluctuations I showed about Casimir effect and the quantum atmosphere effect. So now I will switch the gear to the cavity materials, showing that the cavity vacuum can change the band structure, magnetism, and topology of the materials. Yeah. So why do we use the cavity? In the previous slide, I showed that this vacuum close to the surface, right? It's close to materials that can influence the properties of atoms, spins. But these quantum fluctuations can be enhanced when you have cavity, and that's why we want to use it. And when this quantum fluctuation is enhanced, it has the ability to not only change a single particle, they can change the collective state. So that's why we use the cavity to change the quantum materials. Okay, this is a very simple analog between the cavity and the quantum harmonic oscillator. the left side is the quantum harmonic oscillator, and the right-hand side is the cavity Hamiltonian. So E square, B square means the electromagnetic energy density, right? And times the volume, V is the volume, is the total energy. So right, this V is the volume of the cavity. So you see, these two Hamiltonians is basically the same. Right? You go one-to-one correspond to each other. And actually, when you quantize the EM fields, you're using the cavity as a boundary condition. Okay. So we know that quantum fluctuations in the quantum harmonic oscillator is enhanced if your mass is become smaller. So the smaller the mass, the more easily it jiggles. The quantum fluctuation is stronger. And now here the mass means the volume in the cavity. So the smaller the cavity, smaller the volume of the cavity, the stronger quantum fluctuations in the cavity. And indeed, people make very small cavities and then directly measure the EM fluctuations in the cavities. Yeah, that's the method, the experiment. So using cavity quantum fluctuations to tune the properties of materials has been done by some works. For example, the superconductivity state can be changed by the cavity vacuum. Okay. And the recent very hot topics is that they put in quantum Hall and fractional quantum Hall systems in the cavity, and they find the cavity can change quantum Hall conductance. This is very interesting recent result. And also phase transition. If you have the cavity, putting materials in the cavity and changing the volume of the cavity, they see that the phase of the materials changes. They can change from insulator to metallic state. And also the chemical reactions, because as I said in the first lab, the quantum fluctuation in the vacuum can influence the energy levels. Okay, and then if the quantum chemical reaction is decided by the reaction barrier, which is decided by the difference of energy levels. So the quantum fluctuations in the cavity can also influence the chemical reactions. But all of the previous work didn't focus on, mention even, didn't consider the symmetry breaking. And as I'm from the Condensates community, I know that's how important the symmetry breaking. Okay, so I know that from what I studied about Casimir effect, the symmetry breaking is very important. Okay, so to integrate the cavity quantum fluctuations with symmetry breaking, we can make a lot of things. The first work we did is using the cavity to select carrier molecules. Okay, the carrier molecules in the nature has 200 names. So one left carrier molecule, right-handed carrier molecule. But because of symmetry, these two kinds of molecules have the same energy levels. Okay, it's very hard to select them. And can you find a better and universal way to select a carrier molecule? Okay, our answer is vacuum. When I say this, usually people laugh. It's like a joke. How can you using vacuum to select carrier molecules? And here, by vacuum, I mean it's not this, the trivial vacuum. It's a vacuum close to some material. It's a vacuum in the cavity, okay? Because the vacuum can inherit the symmetry breaking in the materials. So this the vacuum in the cavity have some symmetry fingerprint in it, okay? So by gyrotropic cavity, I mean such cavity break invariant symmetry.
Can you say, so what part of the cavity breaks the symmetry? What is the field that's breaking?
I will show you later.
Okay.
And this is.
But it's in
the general sense that. But I will show specific setup how you break the symmetry in the cavity. And actually, if you do this second order perturbation, it's a very easy thing to do the calculation. And we found that if you have a carrier molecule and you put a carrier in a gyrotropic cavity, and then this cavity vacuum will renormalize the ground state of this ground state energy level of the carrier molecule. So the left-hand molecule without cavity, the left hand and right hand molecule have the same ground state energy. But with a cavity, this left hand and right hand molecule have different ground state energy. And you can use it to select the carrier molecule, and this is you can calculate the efficiency of in the chemical reaction, how much it can generate imbalance of carrier molecules. And we can also use in the cavity to change many body states. So we know that the Pablo said let's talk about this twist ballet graphene. Twist ballet graphene is very interesting because it can generate superconductivity at a magical angle. But this magical angle is not stable. Configurationally, the magical angle is not stable. They can easily relax to other angle and generate an angle disorder. Okay, so the problem is that in experiment it's hard to do that. So how can you still get flat band away from magical angle? Okay, that's what we did. We put this TPG in the carrier cavity that break thermal symmetry. So symmetry breaking vacuum here can renormalize the band structure of this TPG, and then you find that you can still have flat band even away from the magical angle. Originally, 0.1 plus minus 0.1 degree, the magical angle disappear. But here we can at least enhance 3 or 5 times larger than that. So
I was thinking, it's a cavity breaks time reversal symmetry.
Yes.
And why it breaks time reversal?
For instance, you have some ferromagnetic materials to make a cavity, and that's the one of the setup.
But then it will be a field.
No, the field will comes out, and even though you have static field, it won't generate the band gap of this. It won't influence the band structure of the materials. Okay.
But is it materials in the walls of the cavity, or where's the material?
Materials inside the cavity. For instance, you can put the materials. You have cavity here, mirror.
It's
here.
acting like dielectric medium or some medium.
Yes, it's all the. Later I will show you how do they put the quantum Hall bars in the cavity. So, okay. Previous what I showed is basically from the perturbation theory. You can do it using perturbation theory. But here I want to say go to another region. Okay, strong light matter coupling, meaning that the cavity is really small. That the light matter is strongly coupled. Light is not light, matter is not matter. You cannot distinguish light and matter. So what do we do? Well, we find a unitary transformation that can do the job. Because I usually don't show too much about formula, but this formula is I think it's very neat that our students can follow it line by line. Okay, so the first Hamiltonian is just a Hamiltonian for electron near the nucleus. Okay, so the kinetic term VR is the potential that the field by the electrons. The h bar omega c is the photon energy. Okay, so P minus Q A is the vector potential. Usually the vector potential is classical fields. That's why you call the semi-classical approximation. But here the vector potential is quantized. Okay, now we want to diagonalize the system. Okay, or we want to solve the eigenenergy of the system. So when this light matter here, G means the light matter coupling strength. So when this light matter coupling strength is very strong. So what do? We do a unitary transformation, and then you magically find that this light matter decoupled. Okay, this is the momentum part. So all the light matter coupling is encoded in the shifted potential. And Kc is renormalized parameter. So you see, if the light matter coupling G is weak, Kc is very small. Okay, because you see the Kc is here. Okay. If light matter is G is small, Kc is very small, you do the perturbation. If G is very large, Kc also very small, you can still do the perturbation. So in the weak and strong coupling limit, you can both do the perturbation theory. Okay, but the difference, the effective mass, the effective frequency is different in the weak and strong coupling limit. And okay, when you do the perturbation, okay, first order is enough, and then you can find that rigorous result in the weak and strong coupling for hydrogen atom and 2D harmonic oscillator. It's very simple calculations that it's so easy. Then I come to another model in the condensed matter. Also, I use the method I just showed, using the unitary transformation. But here we studied a graphene model, a honeycomb model in the cavity. So the Haldane model is proposed before, but never been realized in condensed matter system because the lattice is so small. You cannot generate staggered flux in such a small scale. But here we show that if you put the graphene, single layer graphene, in the carrier cavity, naturally it is a Haldane model. So the electrons spontaneously feel the staggered flux in each unit cell. And actually, that's when we do the unitary transformation, we get a new Hamiltonian, effective new Hamiltonian, and that's the flux filled by the electrons in the graphene. So it's a spontaneously emergent Haldane model. Just put the single layer graphene in the carrier cavity. And also the spin liquid. Since this is a really powerful method, we can using the cavity to tune the strong correlated phase-field matter. Okay, in the field of spin liquid, there are two things to a very important question. First, how to generate this so-called carrier spin liquid that break thermal symmetry, and you can have fractional excitations. Second, how to detect such kind of order. So we show that we can using the symmetry breaking cavity to generate carrier spin liquid order, and we can using its coupling to a waveguide to detect such a carrier order. Okay. How much do I have? Okay. So now I want to go to this quantum Hall system because there are several new experiments in this direction. So quantum Hall system very interesting topology, and it's quantized the Hall conductance. I don't need to explain that. And when your sample is more clean, you consider, because of interaction, you get a fractional feeding factor. But the recent series, there are many activities to study the vacuum, how the vacuum can change can change the quantum Hall systems, can change the Hall conductance. So, for instance, the first paper just appeared several days ago. So they found that these cavity quantum fluctuations can change the Hall conductance. We know that quantum Hall conductance is very robust, right? So that's beyond our expectation. Why it's such a strong topological phenomena be modified by quantum fluctuations. Okay, so in this work, collaborated with Hans Hansen, we found that we have a theory to explain this phenomena. Okay, the basic understanding is like this. So for high filling Landau levels, the B field is very small. And in experiment, they found there's Hall conductance breakdown. Because in that case, the cavity frequency matched the Landau level frequency, second frequency. So different Landau level mix and Hall conductance breakdown. But in low filling factor, when they have strong magnetic field, the second frequency is very large. The cavity frequency is much smaller than that, so the quantized still remained. But even in that limit, okay, we can still have some other signatures. So for example, even in this case, the Hall conductance is quantized, but the longitudinal conductance is modified in the AC region. So sigma xy is still quantized. Sigma xx is modified. Okay, but why? Why sigma xx, not sigma yy, right? So what breaks rotation symmetry? It's the polarization light. It's the polarization direction in the cavity. Even though it's a quantum fluctuation, there's still direction, polarization direction in the quantum fluctuation. That breaks rotation symmetry. And
You're
also
saying
you
that's
will,
imposed by the quantum Hall?
this one,
That's imposed by the quantum Hall study?
yeah, we put